Hello, my name is Matthew Newland, and this is Homework Assignment 5, Video 2. And in this video, we are going to be finding the max power generation from a turbine with fluid flowing in between the turbine blades. And we're trying to find the max power, or we're trying to prove that the max power that something can generate is with the one-third of that the inlet velocity is going, or the ratio between the inlet velocity and outlet velocity is going to be 1/3. So with that, we are going to come over here with this example over here. So what we're trying to say is that let's just start naming out our parts. So from here, we have a fluid flowing in with a flow rate. So we're going to need our density. And this little circle here is going to be our area, and then we're going to have a velocity. We're also going to have a velocity here as well because the fluid's flowing in. And one example we're just trying to do, at least how this example was done, was through a wind turbine, and we just assumed that this area of air was flowing in through this turbine like this. And then over here, we are going to say that we have a density, area 2, a velocity 2, or an outlet velocity. And then here, we're also going to say that we have a density, but we need a surface area here. The surface area that we're trying to reference here is the surface area of the blades, or the surface area of the blades that are getting blown by this wind. So it's going to be the surface area multiplied by the velocity of the wind at this point. So what do we do now? So what we want to do is start with a momentum balance. So over here, how do we start a momentum balance? So what we're trying to say, so let's just start it out. So what a momentum balance says is that the velocity of the mass flow rate coming in is, or the change in momentum, is equal to the velocity of the mass flow rate coming in, and then the velocity of the mass flow rate going out, plus a force, is equal to that change. At least what we're trying to say in this particular scenario, that this change in momentum, what we're trying to say is that the change in this momentum is going to be 0, which also means that this thing is in steady state. What we're trying to say here is that whatever is going in is going to be coming out, because we would have a very, very big issue if, let's just say, air, for example, this is a wind turbine, if air was getting caught here, that would be an issue, and it wouldn't make a whole lot of sense for our system to not be in steady state, because then we wouldn't be having all of our air come out through the other side. So what do we say? What else can we say from what we said here with this momentum balance being in steady state? Well, like I said before, is that the mass flow rate going in is equal to the mass flow rate going out. Is equal to the mass flow rate going out. And we'll just say that the mass flow rate going in, going out is equal to the mass flow rate of the system. And from here, we want to try to start finding our power equations. So what we want to do now is that we're trying to find our power equations. And how we find those is kind of take what we had from, we're trying to take what we have from up here and try to interpret our data, or at least our givens with this given system, in order to find what our power equations are. So we got to start with force. So our force equation, I'll explain why this looks this way in a minute, are negative F, which is the force that the blades are exerting back onto the air. And that's why that's negative, is equal to the velocity at 1 minus the velocity at 2 multiplied by the mass flow rate. And the power, however, the power equation we're going to use here, or at least one of them, is very similar. It's actually just the force multiplied by the velocity just one more time. So we're going to have by the velocity at this point on our system. So it's going to be the same thing. Density, velocity squared. So this is our power equation, or at least one of them. And in order to find another power equation that we're trying to do here is trying to find a kinetic energy balance. We found our power in terms of our forces that are happening here. But we need to find another power equation in order to set them equal to each other in order to get a better balanced equation, a better balanced system. So we're going to come over here. So what we're trying to do next is get a kinetic energy balance. So kinetic energy balance, where our change in kinetic energy divided by our mass multiplied by the mass flow rate. And that's another way of finding another power equation, which is also going to be in joules per second. That's what these units cancel out to. So taking that into account, we also have another equation we can use. So our other equation for power is also going to be kind of in terms of a similar equation we use with the Bernoulli's equation. It's going to be set up in a similar way, where it's going to be the velocity. Sorry, I'm not writing this big enough. The velocity at 1 squared minus the velocity at 2 squared over 2. Well, I'm writing this very poorly. Divided by 2, multiplied by the mass flow rate, which is going to be what we had up here, except without that second velocity squared. So it's going to be multiplied by our mass flow rate. So this is our second power equation. What we want to do now is set them equal to each other. And that's going to give us and this is going to help us find it's going to help us relate these two power equations in order to find what's going on, or find a relationship between these three velocity values and what's going on. So what is this saying? So let's set both of these power equations equal to each other. So we have this one here, which is going to be velocity at 1 minus our velocity at 2 times our density times our surface area of the blades multiplied by our velocity at the blades. And then that is going to be equal to what we have down here. So that is then going to be velocity at 1 squared minus our velocity at 2 squared divided by 2. And then it's going to be our mass flow rate again. And from here, we can then begin to start canceling some of our variables out. So what we can immediately start canceling is this density and this surface area. And we also have another velocity in the middle section here. So we're going to cancel that out, cancel this out, cancel that out. Cancel our density, surface area, and then get rid of this exponent up here. And what we found here is that if we divide this entire equation by our V1 minus V2 in parentheses, we can actually get this middle section velocity by itself. So this says that the velocity in the middle is going to be this equation here. And if you notice, is that we can kind of expand this out even farther too. So we're going to have V1 minus V2, V1 plus V2, or velocity at 2, is going to be 2 multiplied our velocity at 1 minus our velocity at 2. And if you can see, we can cancel both of these out now. And then we're going to have a new velocity equation. We're going to have this velocity equation be too large. So as you can see, the velocity in the middle is almost the average between these two, and that's how this relationship between these two velocities are working together. From here, we'll rewrite our equations from before that we found before. So we have our velocity at the turbine is equal to velocity at 1 plus the velocity at 2 divided by 2. And then our power equation from our kinetic energy balance will be velocity at 1 squared plus the velocity at 2 squared, or sorry, excuse me, not plus, minus the velocity at 2 squared divided by 2 multiplied by our mass flow rate. So it's going to be density, surface area, and velocity at the turbine. And from here, what we want to do now is then we want to substitute this V with this velocity here. So what we can do now, just cross that off. So we'll have a new power equation as such. So our new power equation will be our power, and we'll just rewrite what we have right now. But we're going to substitute this in now, so it's going to be V1 plus V2, excuse me, writing very small. And then, since we have this 2 on the bottom, we will have a 4 on here as well. So what happens now? So what happens is that we can multiply. What we want to do now is then multiply this out, and then we're going to end up finding a kind of a trend here with our variables with velocity. So let's multiply this out. So this new power equation is going to be, so we have a couple constants here, so we're going to bring that out front. So it's going to be our density. So it's going to be our density, our surface area divided by 4. And then we're going to have a very long equation being brought out here. So it's going to be our velocity at 1 cubed plus our velocity squared at 1 minus our velocity at 2 minus, and then that's when we start multiplying our second portion here. So it's going to be our velocity at 1, our velocity at 2 squared minus our velocity at 2 cubed And this is going to be our equation. And one thing we want to do now is that the one thing we're trying to find is how is there a relationship between our starting velocity, or not our starting velocity, but our inlet velocity and our outlet velocity. So what we want to do now is that we want to put this problem in a scenario where we can take the derivative of it so we can find the max output. So what we're going to do now is divide this entire equation, or we're going to draw out from this entire equation a velocity at the inlet cubed, and we're going to divide this entire equation by it. Or we're going to draw it out from this parentheses. So we're going to have a new equation as such. So we're going to have power here, and then we're going to have density times our surface area of the blades, and then we're going to have our velocity at 1 cubed divided by 4. And what that leaves us with, that will lead us with 1 plus our velocity at 1, well, it's going to be, so that's going to divide up both of them. So it's going to leave us with a velocity 2 up top, velocity 1. And then we'll do the same thing for the rest of the side. So we're going to have a minus 2, 1 squared minus our velocity at 2 over 1 cubed. And what we want to do now is then try to get this into a form where we can take the derivative of it. So how do we do that? Well, if you notice, we have kind of a common, we have a common variable over here, which is the velocity of the output divided by the velocity of the input. And we have that in various exponents, which is good because we can take the derivative without everything being canceled out, because it would have been a constant. So what we want to do now is set an r value, or just some random variable. We're just going to say r, because why not? So our r value is going to be V2 over V1. And we'll just rewrite it one more time before we take the variable to see what our form is going to look like. So we'll start replacing all these variables with r. Sorry, I'm writing very small today. So this is our new equation. So this is our new equation. And then we can now take the derivative of this entire equation with respect to r. So we're going to come up here and we're going to do exactly that. So what we're going to say now is that our change in power with respect to r is going to be equal to, well, getting our constants back. So it's going to be our density times our surface area times the velocity at the inlet cubed divided by 4, and then in this parentheses is going to be 0, because that's a constant, plus 1, and then we have 2r minus 3r squared. And then in order to find the max and find the max output of this equation, we have to set this equal to 0. Because that's the derivative, we'll find the slope. So what we can say now is that we can then bring this sort of, this equation in here, or these variables in this bracket down, and try to figure out what the root is going to be, because these are just constants. And we're not going to include those when we're trying to find our root. So we're going to bring these down, and we're going to get a new sort of set of variables where it's going to be 1 minus 3r, and then it's going to be 1 plus r equal to 0. And since we don't want this one, because that's going to end up with our r being negative, we don't want that. So we're going to have an r value of 1/3. And if you recall, is that our r value is our velocity at 2 divided by our velocity at 1, or the outlet and input. So this means that this is the ratio that we found. And kind of just doing a prior calculation before I started the video, technically our power, if we plug 1/3 back into this equation, here, we're actually going to get something like this. Our density times our surface area multiplied by 1, our velocity at 1, and then since we're actually putting numbers now, we're going to have 8/27. Or more importantly, it rounds up to 1/3. And this kind of proves our Betz' law, because our ratio between the input and output velocities is going to be 1/3, which is going to very much correlate with our power, because technically our roundup here is going to be 1/3 as well. So this is what we call Betz' law, and this whole scenario that we did here proves that at maximum efficiency, you are only going to get 1/3 of the power. That you're only going to get 1/3 of the max power you can get there.